This episode of Real Engineering is brought to you by our very own graph paper notebooks, now available in 3 different sizes. In the not too distant future, you could be flying in one of these incredible planes, a configuration you've likely only ever seen used in high-tech military aircraft like the B-2 Spirit. But this plane won't be used to carry weapons. It will be used to ferry hundreds of passengers around the world and use vastly less fuel in the process. This blended wing aircraft is capable of causing a seismic shift in the airline industry, greater than any other technology advanced before it. Over the past 60 years, airliners have evolved drastically. While the tried and tested tube and wing layout has remained largely unchanged, less obvious innovations have allowed commercial airline travel to become an unremarkable part of everyday life. One statistic illustrates the continual evolution of airliners better than any other. This graph shows a downward trend that has been caused by unyielding efforts to innovate. This line represents the average fuel burn per passenger per kilometer. Engineers have managed to find ways to reduce the amount of fuel these planes burn by nearly 50% over the past 5 decades, allowing travel to not only get cheaper, but more eco-friendly per passenger kilometer travelled. From improved wing geometries, like the eclectic mix of wingtip designs we see across different airliners, the split wingtips of the 737 MAX, the wingtip fences of the A380, the blended winglets of the A350, and the raked wingtips of the 787. Each design attempts to minimize the vortex drag, the drag caused by mini tornadoes forming at the end of each wing. These tornadoes cause more fuel to be burned. These wingtip devices alone can reduce airliners' fuel consumption by up to 6%. Engines have of course undergone radical changes, the most obvious changes being the continual increase in engine size over time. There are uncountable innovations, and many of them are hidden from view. However, one thing really hasn't changed all that much in those 5 decades. The tube and wing has stood the test of time. The first time we saw this format take to the air was the Boeing B-47 Stratojet in 1947. This may look to you as a perfectly normal plane, but for the time it was unique. With a long skinny fuselage, long and narrow swept back wings with jet engines mounted in pods under the wing. This plane was incredibly capable and popular with the US military, and its success resulted in Boeing investing vast amount of money into perfecting the format and creating assembly lines to churn them out. This is the template of the modern airliner, and Boeing soon used it to develop the world's first successful commercial jet airliner, the Boeing 707, which began the tube and wings domination of the commercial airliner industry. Its advantages made it a difficult king to dethrone. The circular cross-section is perfect for repeated pressure cycles as the plane rises up and down through the atmosphere, sometimes multiple times a day. It's easy to create variants of each plane model by simply adding or subtracting tube sections to lengthen or shorten the plane. This allows aircraft companies, like Boeing, to quickly offer variants of existing planes without forcing pilots to retrain on entirely different aircraft and gain FAA approval for an entirely new plane. Yet, the tube and wing layout may be the last thing standing between us and truly sustainable, eco-friendly air travel. NASA, Boeing, and Airbus have all dedicated substantial resources into investigating a new kind of plane, the blended wing. To understand why, we need to look at some of the disadvantages of the tube and wing configuration. Let's take a look at a typical airliner like the 737. Its center of gravity is located about here. This is the point at which all lift will act around, like the fulcrum on a seesaw. Our center of lift is located slightly behind this. This would force the plane to pitch downwards without a counteracting downwards force further back on the plane, which is exactly what a horizontal stabilizer provides, downwards force. This balancing force keeps the plane flying level, but a downwards force is obviously not what we want. We are trying to fly. We want upwards force. This is wasted energy. At cruising speed, that downwards force accounts for around 5% of the total weight of the plane. This increases the lift the actual wing needs to provide, which increases the induced drag the plane is generated and pushes the fuel consumption up significantly. It gets worse. Induced drag is the drag created as a byproduct of lift, but there is another form of drag, parasitic drag, which is a combination of skin drag and form drag, with skin drag being a function of the total surface area of the plane and the form drag being a function of the total frontal area. We refer to the total surface area of the plane as the wetted area, which has its origin in naval engineering, the wetted area referring, rather obviously, to the area of the ship underwater. While the tail is providing that downwards force at the cost of the wing needing to generate additional lift, it is also drastically increasing the plane's wetted area. The tail of a conventional airliner accounts for between 25 and 35% of the total wetted area. This again increases fuel consumption significantly. By eliminating the tail, the blended wing body can benefit from a 27% decrease in fuel consumption. To put that into perspective, if every commercial airliner became a blended wing body, that could reduce the world fossil fuel consumption by 26 billion gallons a year. This fuel-saving potential has attracted the attention of every major aerospace company. The vast majority of major improvements in the airliner manufacturing industry has focused around relatively minor savings in fuel. If your plane can save an airline 5% in fuel spend, they will choose your plane over the competitor. Imagine what a 27% decrease in fuel spend would do. This is exactly what McDonnell Douglas was hoping for when they started the development of their own blended wing plane in a Hail Mary play to save their company. As sales declined as a result of strong competition from Airbus and Boeing, before eventually being bought out by Boeing. Boeing continued their work on the technology alongside NASA with the experimental X-48. The X-48 never developed into a full-scale aircraft. Instead, various different subscale models, both powered and unpowered, were developed to investigate one very important problem with the blended wing aircraft: stability and control. This radical new design required the engineers to develop new models for control, particularly because removing the tail removes a critical stability feature. As we explored already, the tail provides a critical service in providing a balancing force for the offset center of gravity and center of lift. But why can't we just place the center of gravity and center of lift at the same position? That would eliminate the need for a balancing force. Well, that ignores the fact that planes are constantly being knocked out of straight and level flight by turbulence, and the tail is constantly working to counter these forces to push the plane back into the desired direction of flight. Take the horizontal stabilizer as an example. It has a negative angle of attack, since its goal is to provide downward force to counter the forward center of gravity. When a gust of wind knocks the plane upwards, this angle of attack decreases, and thus the downforce decreases, allowing the weight of the nose to pull it back down. This is why the center of gravity is intentionally placed forward of the center of lift, as it itself acts as a restoring force. Conversely, if the plane pitches down, the angle of attack increases and increases the downforce, which forces the tail of the plane back down. The horizontal stabilizer provides passive pitch stability, requiring zero input from the pilot. Without these stabilizing forces, a blended wing body would need constant active course correction, with control surfaces constantly wiggling to balance the loads, like a person trying to balance a broom on their finger. Constant tiny movements to keep the center of mass above the finger. But a human will eventually fail. It's not a question of if, but when. This is why early attempts at flying wings, like the YB-49, failed. Humans simply cannot reliably fly them. Then, fly-by-wire technology was introduced and allowed unstable planes, like the B-2 Spirit, to enter service. You can see the control surfaces of the B-2 working hard to keep the plane flying level in many of its refueling videos. It's possible to fly safely like this, but an active stability control system is always going to be less safe than a passive one. There is very little that can go wrong with a static control surface like this, beyond the tail surface breaking off, which is essentially impossible with regular maintenance. The system is foolproof. However, active stability has numerous points of failure. The control surfaces with their various moving parts could fail, the sensors feeding the computer with data could fail, or the software itself can fail. The one and only loss of a B-2 was caused by a failure of airspeed sensors, which fed the control computer inaccurate data, telling the computer that the plane was pointing downwards. So, the computer responded by pitching the plane up at a very low speed, causing the left wing to stall and lose lift, resulting in the wing dropping and striking the ground. Thankfully, the two pilots managed to eject in time, but the loss of a $1.4 billion aircraft is a heavy price to pay for faulty sensors. This happened in 2008, but we have much more recent examples of failures, and they occurred in the civilian airline industry. The 737 MAX's launch was marred by failures in fly-by-wire technology. The 737 MAX was fitted with larger engines than its predecessor, the 737NG. These engines were fitted further forward and higher up, as they could not fit under the wing in the same location without lengthening the landing gear. These new engines and their new position altered the flight characteristics of the plane, moving the center of gravity drastically. Typically, this would be accompanied by alterations in the airframe to ensure passive stability. But Boeing, in an act of corporate greed that I'm entirely sure the engineers in the company objected to, decided to skip this step as it would require the plane to be recertified, which could add years to the delivery dates and require airlines to retrain pilots. Instead, Boeing installed flight software called Maneuvering Characteristics Augmentation System, or MCAS, to automatically correct this stability issue. However, the system was designed incredibly poorly, requiring just one sensor to display a high angle of attack value to activate MCAS, and automatically cause the plane's computer to take over and pitch the plane down. On 2 occasions, a single faulty sensor providing erroneous data caused MCAS to force the plane into a nosedive. This could be chalked up as an accident caused by faulty sensors, but in reality, it was faulty software that should not have been relying on a single sensor to trigger. Engineers should expect their sensors to break at some point. This is why redundancy in design is needed, with multiple sensors all checking each other's work. The archaic computers that got us to the moon managed to do this. The fact a modern plane like the 737 MAX couldn't is criminal. Fly-by-wire systems can be safe, but it will require multiple levels of redundancy, and as we saw with the 737 MAX, it takes only 1 or 2 instances of failure before the flying public will lose trust in a plane's reputation. With a radically new design, like the blended wing, a single crash could cause the general public to associate the design with danger. It's critical that these systems be coded and designed perfectly, which is exactly why the X-48 models were created. These models were used to gather data on flight performance and allow the engineers to design and develop new flight control algorithms to ensure the plane is safe. These models were designed to be scaled up to a full-sized passenger or cargo plane version, with much of the development focusing on creating large internal volumes. This layout does come with some drawbacks, the most obvious one being the lack of windows. The only windows in the plane will be on the main cabin door up front. This is a bit of a bummer for those of us that enjoy window seats, and worse still for those of us that are claustrophobic. To alleviate this slightly, designers have proposed having high-quality cameras feeding screens at each seat, which has been a feature already implemented into Emirates first-class cabins that aren't next to actual windows. But I think we can all agree it's not quite the same. While others, like the Flying V concept, have proposed a variation of the flying wing design where windows could stretch further back along each wing. Some have expressed concerns that an emergency egress would be difficult and slow, likely because it feels like an exit is further away when you can't see the outside of the plane. Exit doors for the 450 passenger version of the plane are located in these locations, with each of the 6 aisles having emergency doors located at either end. With the short fuselage, exit doors are much closer than a traditional airliner, and the doors are not located at an awkward 90-degree angle to the aisles, which will help prevent traffic congestion at the turn as people panic to get out. This, of course, provided airport infrastructure changes to accommodate them, means the blended wing will have much faster boarding and deboarding times. We have all been there when a single person manages to clog the only exit aisle as they dither around with their bags. With 6 aisles, no one person can stop the entire plane from deboarding. This layout, with a much wider and shorter fuselage, comes with some fantastic structural benefits too. A typical tube and wing aircraft spreads the internal volume over the length of the aircraft. So, if we map where the weight is located along the lateral y-axis of the aircraft, it would look something like this. The vast majority of the weight of the aircraft is centered in the fuselage. Now, if we map where the lift is located, it would look something like this, with the vast majority of the lift being located over the wings. This is a problem, because this introduces bending stress at the root of the wings, where the downward force of the fuselage meets the upwards force of the wings. To withstand this bending stress, tube and wing planes need to add a significant amount of structural reinforcement. This adds weight, and thus, once again, increases fuel consumption. Now, let's look at the cross-section of the proposed full-scale 450 passenger version of the X-48. This layout, with a much shorter and wider fuselage, results in a weight distribution that would look something like this, with the weight much more evenly distributed along the y-axis of the aircraft. Now, if we map the lift distribution, it would look something like this, with the lifting body fuselage actually contributing to the total lift of the plane. This means that our lift and weight are largely located over the same areas, reducing airframe stresses dramatically, with up to 50% lower bending loads. This means the plane can reduce the reinforcements required to resist these loads, and thus total weight. This lift distribution is also near the optimum to minimize the induced drag caused by vortices forming at the wing tips. This occurs as a result of high pressure air under the wing mixing with low pressure air above it. By creating an elliptical lift distribution, this undesirable mixing is minimized, once again reducing fuel consumption. However, there is one problem. It's difficult to design this internal fuselage to resist pressure loading. As the plane rises through the atmosphere, the air outside the plane lowers in pressure, while we pressurize the inner cabin to a comfortable level for the passengers. This causes an internal pressure that causes the fuselage to expand. The circular fuselage of the tube and wing is the optimal shape to resist pressure. Circular pressure vessels expand equally in all directions, and thus the skin of the fuselage is primarily in tension equally around the circumference. With square interiors like this, the pressure would cause the roof to balloon outwards, with large deflections in the midspan between bulkheads, and stress concentrations at the bulkheads between each cabin section. This is not ideal. We have already seen what happens to planes when repeated pressure cycles are combined with stress concentrations like this. The very first video on this channel discussed the problems with the de Havilland Comet, an early jet airliner which featured square windows. These windows allowed stress concentration to build around the corners of the window, which, over repeated pressure cycles, allowed cracks to gradually form as a result of metal fatigue. This caused 3 fatal mid-air disintegrations of the fuselage, before the problem was identified and fixed by changing the windows to an oval shape and reinforcing the area around them. Designing a pressurized aircraft like the X-48 with standard aluminium would be incredibly cumbersome and would require intensive inspections and maintenance to ensure no dangerous cracks were forming. However, thanks to some modern manufacturing techniques, we can design a plane like this with relative ease. Carbon-reinforced plastics are the future of airliner manufacturing. We've already seen the benefits this material has provided the 787. Its fuselage is formed by wrapping a carbon fiber tape around a fuselage mold. This is then placed inside an autoclave oven to cure a plastic resin that will bind the carbon fibers together to form one solid structure. Thanks to the stiffness and strength afforded by the carbon fibers, the 787 can pressurize the interior to a much higher level, a pressure equivalent to about 6,000 feet in altitude. A typical airliner has air pressure equivalent to about 8,000 feet. If you've ever felt bloated on a long journey, the lower air pressure is why, because your stomach is literally expanding due to the lower outside pressure. The lower air pressure also decreases the amount of oxygen your body can take in, which exacerbates the effect of jet lag. You may have also noticed the absolutely massive windows on the 787. These huge windows create large stress concentrations in the fuselage, but thanks to carbon-reinforced composites' relative immunity to fatigue, the engineers were able to make them bigger without worry of crack growth causing failures. So, the key to building the X-48 will undoubtedly be carbon composites. The designers of the X-48 proposed 2 potential structures to deal with this internal pressure cycling. The initial concept proposed separating the skin from the pressure vessel, allowing the pressure vessel to be shaped with arches between bulkheads. The other design simply called for a thick, composite sandwich structure that would act as both the skin and the pressure vessel. Ultimately, the second design was preferable, as any breach in the inner arched pressure vessel could cause the thinner outer skin to break away completely, and thus the outer skin on this design would also need to be capable of resisting the internal pressure, making the internal pressure vessel entirely redundant. We have plenty of experience in designing a plane with these kind of materials now. In fact, the B-2 was primarily constructed from a carbon graphite composite, which not only allowed the engineers of the B-2 to precisely mold the plane to the optimum shape to scatter incoming radar, but the material itself absorbs more radar waves. Boeing was the primary subcontractor for the construction of the B-2, manufacturing much of the aircraft's skin using an automated tape laying process, which they now use for the 787. This process will allow manufacturers to optimize the shape of future blended wings, and incredibly will result in a plane with far fewer parts than a traditional airliner, up to 30% fewer parts, which, after initial investments in creation of new manufacturing tooling, should result in cheaper planes. One impressive example of this in action is the Northrop Grumman BAT surveillance drone developed by Swift Engineering, whose fuselage consisted of just 3 parts: an upper skin, a lower skin, and a payload cover. Just 3 molds required to build an entire fuselage is incredibly impressive and cost-effective. It's clear that the technologies needed to facilitate the introduction of a commercial blended wing have reached maturity. Up until now, the incentive to invest vast amount of money into a new airframe was low, but that may soon change. Aeronautical engineers have seen the potential of blended wings for over 7 decades, with potential benefits like 15% lower total takeoff weights and 27% lower fuel consumption over traditional airliners. It's clear why the idea has never truly been forgotten. The final push the industry needs to finally adopt the blended wing may come with the need to eliminate hydrocarbon fuels altogether. As we learned in our previous episode, engineers are struggling to find space within the airframe of tube and wing planes to incorporate hydrogen fuel tanks, but blended wings with massive internal volumes and low fuel consumption would make this job vastly easier. If hydrogen fuel wins the battle to replace fossil fuels in the aviation sector, there is no doubt in my mind that we will soon be seeing these futuristic planes landing in airports all around the world. Richard Walls, one of NASA's strategic technical advisors for advanced aircraft, even stated we could soon see these planes in service by 2040, ushering in a new era of air travel. As I was researching this topic, I came across a lot of new information I wasn't familiar with. It takes me time to absorb and understand new topics like this, and my method for learning has always centered around taking meticulous notes with carefully drawn diagrams. The process helps me slow down and focus on the information I'm taking in, instead of just blindly reading. To me, this almost meditative process is critical to creative learning. Not just reading and memorizing what you learned, but truly understanding it and incorporating it into the creative kaleidoscope of your mind, where new, coherent ideas form seemingly at random. To me, this is the core of what engineering is about, the junction of science and art. And every artist needs the right canvas. We started with just the Moleskine style notebook 2 years ago, but since so many of you have been repeat customers, as you fill in these notebooks with college notes, we wanted to offer a larger college notebook version. It's larger and has more pages, all lined in a metric 1 centimeter grid. I designed it with the spiral on top to allow you to use the spiral bind to shield your precious notes as you attempt to shove the notebook into a crammed backpack. We are currently doing a bundle where you can get both the college notebook and Moleskine style notebook together with a free pocket-sized field notes version thrown in for free. And on top of that, you will get a free month of Nebula with every purchase, so you can watch my original Logistics of D-Day series for free, along with all the other wonderful original content on Nebula. A link for that is available on screen right now and in the description. If you are looking for something else to watch right now, you could watch my last video about the uncertain future of jet fuel, or watch Real Science's latest video about the rise of hybrid animals in the wild.